Okay, good day everyone. So today I'm going to actually demo for my FIP, which is the Agriculture 4.0 indoor ginger growing with IoT based LED system. So noted that this demo actually I will remove the STM32 connection, where we actually can see that we have ESP32, STM32 and STM8. So for this demo I will only directly connect the ESP32 to STM8 due to time constraint where I don't have time to actually build the STM32 circuit. Okay, so this will be the overall circuit schematic that later I'm going to demo with. Okay, we can notice that we have a touchpad power supply, which is a 14 volt, to three different STM8 microcontroller. As you can see that this red and black, it has a 14 AC, is supplied to these three STM8 circuit. So we also have a 5 volt breadboard power supply, which is here. So we use the color code of pink and black. So this one is actually used to supply the 5 volt for communication, which we have a RS485 circuit here and these three STM8 circuit. So we need to power up with 5 volt supply. And the reason why we actually use the 5 volt supply here is because the communication circuit, we actually have a different power domain. So we have opto isolator to actually separate out. So we actually need to have a extra 5 volt supply to actually supply the voltage, so that they can run the RS485 chip over here. So we also have a RS485 communication at the communication circuit from here, here and here and here. So every STM8 circuit we have a communication circuit, and with the ESP32 circuit also we have this one. This one is actually we use the RS485 for the communication between the ESP32 and STM8. So this RS485 will actually convert from differential pair to non-differential pair, so that we actually can transmit longer with less noise. But the cons is we need to actually power up with the power supply. You see the 5 volt breadboard power supply. We need to use the 5 volt to power up that chip. Okay. So the transmission line, the A and B, is actually a green and a blue. So we also have a ESP32, which is the LED main controller. Later we're going to demo, we're going to send a packet, a command from PC to the ESP32. So this one will be the one actually control which packet to send to either one of the microcontrollers. So it actually connected to PC through the USB cable, so that we can see the console on our PC. I will show it later. Okay, and then we also have a LED bar. So we have two different sets of cable. You can see the DIMM plus, DIMM minus one set, and the VO plus, VSense and VO minus is one set. So DIMM plus and DIMM minus is a yellow and black color coded cable. So we actually use to control the intensity of an LED light on the SMPS. So this DIMM plus and DIMM minus we actually can control on three-way. Either use the 10 volt, 0 to 10 volt, or we use the 10 volt PWM circuit. So if the period is larger, then the intensity is higher. So this DIMM bus is actually connected to the output of the PWM. You can see that the output of PWM. And then the DIMM minus is connected to the ground of this STM8 circuit. And we also have a Vout plus, and then Vsense and the Vout minus. So Vout plus is actually connected to the voltage sense circuit, as you can see, the voltage sense circuit, to actually retrieve the voltage level. And then Vsense and the Vout minus is actually connected to the current sense. So when the power going through here, right, and then it needs to go back to the VO minus, so we will go to this Vsense, and then the current sensor, it will go to here, and then you come back here, Vout. There will be also a thermistor to actually detect the temperature of the LED. Okay, so let's go to the next page where we can see a clearer idea. So you can see the voltage sense circuit, the current sense circuit, the Vsense and the Vout. So here we have a small sense resistor to actually generate a small voltage, and then we amplify it using an op amp. Okay, so this is the SMPS. So we power up with 240 volt AC. So with a normal plug, and then we turn it on, and then we connect it, something like that. Okay, so we also have actually a mock circuit, because we have 3 circuit but we only have these 2 with the LED and another one without the LED. So this is also because due to the time constraint, where we actually does not connect to a SMPS with the LED, but we actually will replace with the blue LED, and then the voltage sense will put the potential meter, and current sense is also potential meter. So later, and you see in the demo, I can turn the potential meter, and then you can see the reading is different. So in the real case, the power supply for the 12 volt, we are not going to use the touchpan power supply in our farm, but we use something like that, which is a power supply, which will be implemented on our circuit board afterward. Okay, so before I show my demo board in my lab, so let's go through a bit on my STM8 circuit. Okay, see, this is my STM8 circuit. So this is my microcontroller STM8. So we have the 20 pins, and we set recap and etc. So we have enable the UART pin, and the current sensor, voltage sensor, and the temperature sensor. So the transmit and receive here. Okay. And then we also have a voltage and current for the sensors, LED plus, LED sense, and LED minus. Okay, so just now the 3 cables, they are the color coded cables, orange, purple, and gray, the VOut plus, VSense, and VO minus. So we also have those sensors like temperature sensors. We have a thermistor over here, and then we have a resistor here. We use the voltage divider circuit to actually get the temperature sensor value, and then we use an equation to actually calculate it. And then for the current sensors, we will actually detect the current from LED sense to LED minus. Okay. Then we get the voltage across the sense resistor, and then we amplify it using this op amp, non-inverting amplifier circuit. So the gain is around 169 something. And then we also have a voltage sensor. So here will be the LED plus. LED plus is a VOut plus, the orange color cable. So we actually use the voltage divider circuit to actually get the voltage value from maximum 0 to 80 back to 0 to 5 volt. And then 0 to 5 volt we will convert into a digital value. Then we will calculate back the real voltage over there. Okay. So we also have the switching circuit for PWM from 0 to 5 volt, from 5 volt to 0 to 10 volts. So this is because our microcontroller, we only can set around 0 to 5 volt. The maximum is 5 volt. So if we want to get a 10 volt maximum, we need to build some circuit like this, as the SMPS will actually detect the PWM signals with 10 volts. Okay, so we also have the 2 LDO in our demo, but in the real design we only have 1 LDO, which is from 12 volt to 5 volt, because the supply is already 12 volt, it's not the 14 volt. Okay, we also have the opto isolator, which is a communication circuit. So we use the opto isolator to actually separate the power domain between MCU to prevent some tragedy like short circuit, and then one of the microcontroller burn. If we actually separate the power domain, other microcontroller will be still remain protected. So if we mix all the power domain together, if one of the circuit short circuit, and then it will also cause other microcontroller to short circuit. So we also use the RS485 module to actually communicate between microcontrollers, where it's a non-differential differential pair, and then here is non-differential pair, where it able to actually transmit longer and less noises as the signal is actually floating. So let's go to our video recording for the overall schematic design. Okay, now I'm going to show you my demo board in the lab. Okay, so we actually have a 14 volt power supply to actually power up this 3 board, 1, 2, 3, where they actually have a LDO, which is a low voltage dropout, to actually regulate the voltage to 12 volt and then to 5 volt. So that one I'm going to discuss it later. Okay, so I'm going to continue, and then you can see the red and brown color coded twisted cable is actually connected to this to LDO. Okay, so afterward we have a breadboard power supply. This is actually a 5V external to actually supply the opto isolator on the board. Okay, so you can see to supply the RS-485 communication devices on here. This one I will discuss it later. You can see this pink color coded cable is connected here. Pink color plus white. So pink color is 5V plus, and then white color is ground. Okay. So and we have a ESP32 over here. You can see there's actually USB cable connected to the PC. So this one is actually for the serial use. And then this ESP32 will connected to this small chip, which is called MAX1487, which is a RS-485 devices. So RS-485 devices is a communication devices which they convert from a non-differential pair to a differential pair. So the differential pair is something like this color. So the blue is A and the green is B. You can connect. They are connected to all these three board. You can see the first one, and then the second one, and the third one over there. You can see. Okay. Okay, so we also have connected to two sets of LED. So this one is a switch mode power supply, and here also a switch mode power supply. So they have two cables, you can see here. So this yellow and brown cable, as I discussed just now on the diagram. So the yellow is actually a dim plus, and the brown is a dim minus, which is actually to control the intensity of this LED. And then we have these three cable twisted together. Oh, not here, sorry. It's here. Three cable twisted together. Okay, so the orange one, right? The orange one is actually connected to the water sensor, and then which is a VO plus. And then the purple one, you can see the purple one. The purple one is actually a V-sense. That means before this LED, the voltage going back to the switch mode power supply, we will go through this one. Sense. We will go through into this water current sensor, and then you will go back into the V out minus. So this one, the gray one, is a V out minus. You can see it's going back to here. You can see this blue cable is actually a V out minus, as you see on the board. Oops. Blue V out minus. Okay. So in conclusion, we have three sets here: 1, 2, and 3. So the difference is this one is a green. Because we actually don't have a green color currently, so we actually use a red to replace it for this demo. So we actually use this one as a green, and then this one as a red, and then that one as a blue. But that one is a simplified version where we don't have a LED. We just want to have one set of communication. As you can see, it's actually a blue LED. This one is generating a blue LED. And then we replace the voltage sensor and the current sensor become a potentiometer, so we can adjust it later. But this one I will show the demo later. Okay. Okay. Let's talk about the STM8 circuit right now. So we actually have this red and brown, which is a 14V supply from the touchpad power supply here. Touchpad power supply. Okay. So we actually have a 14V and then a ground as a chocolate color, and then the red color will be the 14V. Okay. So we have a LDO there. I zoom in a bit. Okay. We have a 12V regulator to actually regulate from 14V to 12V, and then we have a 5V regulator. So it's actually to regulate into 5V. So this 12V we actually use in two circuit, which is a current sensor and the PWM circuit. We're going through that later. Okay, so let's talk about sensors now. Okay, this will be our temperature sensor. You can see the thermistor cable. Okay, so we zoom out. You can see the cable is actually sticking on this LED light. You can see the LED light over here, and then you can see this is actually the thermistor, okay. And then it goes back, and then we have this. This is actually the voltage sensor. So this yellow cable just now I mentioned, this yellow cable is actually the V plus of the power supply, the LED power supply. Which one? Yeah, this one, yes, this one, the orange color cable. Okay, so we have this one. So this one is a PWM circuit. Okay, this PWM circuit is actually the switching circuit to control the intensity of the LED. So because LED we can actually use three methods. The first method we actually can use 0 to 10 volts. That means we can use a digital to analog converter to convert the value to become an output signal. Or the second one, we actually can use a PWM signal from 0 to 10 volts. So we take around 2 kilohertz to control it. That means if the period is longer, then the intensity is higher. So if it's smaller period, then the intensity is lower. Okay, so you can see there will be a diodes, MOSFET, and then this will be the diodes. Again, here will be this one is a BJ MOSFET, and then this one is a Schottky diode, and then this one is a capacitor, and then here will be the output of the signal. You can see it's a yellow and a brown combination. Okay, so I move it out. Okay, sorry. Okay, here is the signal going in here. Okay, going into the PWM, into the power supply, and then the power supply will generate a equivalent voltage across it. Okay, so we also have this current sensor. Okay, sorry. Okay, this current sensor is actually, we have this one is a op amp, so it's power on 12 volt instead of 5 volt, and then we have a V-sense resistor, so it's around 0.01 ohm. So the reason why we actually use those small resistor is because, you know, power is equal to I square R, right? So if we use a very large resistor, right, the power across here, power dissipated here will be very large. So we, instead of using so large power resistor, we use a very small resistor to actually sense the current across. So this purple color will be the V-sense. Just now, okay, I'll show you the V-sense. Okay, V-sense, which means before he goes back into the V out, it connect to here, the V-sense, and here will be connected to this sense resistor, and then the sense resistor will have a connection to actually connect to the input of the op amp. Okay, this one is the input of op amp. So they will actually take the voltage generated across this sense resistor, and then it will convert it to become a digital analog value to be read by these microcontrollers. Okay, and then we have a Zener diode here to actually avoid the voltage cross more than 5 volt. Okay, and lastly we have this. Okay, we have this communication circuit. Okay, as you can see, there will be a blue and green cable. Just now I mentioned that this one is a different non-differential pair, so he will connect it back into these RS-485 devices, and then these RS-485 devices will be change back all this signal back to a non-differential pair. So, and then we will go through this three opto isolator. Yes, and then one is for receive, transmit, and another one is a enable pin. because this RS-485 we can set either we want to receive or transmit. So in order to actually set it, we need to have this enable pin. So you might ask, why we actually need this opto isolator? We just connect it together. Why we need to put this opto isolator? It's because, right, so for example, we have 32 sets of STM8, STM32, and then 96 sets of STM8. So in case, unfortunately, one of the circuit short circuit and then he burn. So if they are all connected together through this A and B line, and then this 5-volt supply, we will actually burn the whole circuitry farm. Like all these STM8, STM32 will be all burned because they are all connected together. So in order to actually avoid that, we actually use this opto isolator to actually avoid it. So that means if here short circuit, you won't affect others. You only affect the circuit inside. This circuit is still will burn, but the circuit outside here for the next board, right? For example, okay, hold on, let me see. So for example, we have 3 boards here, right? So if this board burn, but this board and another board won't be affected because they're actually isolated. They have a different power domain. So this is a reason why we actually use opto isolator instead of just connected together. Okay, so lastly, we have the microcontroller here. This one is a STM8 S003. So we have 20 pins over there. We can connect all the thing we run. This one, this few pin will be analog, and then this leg, right, we actually use to program using the ST-Link. Yeah, ST-Link here. Okay. So that's all for my board showing. So let's go to implementation demo. Okay. So now let's go to the demo part. The software that actually now currently using is actually our Postman software, where they're able to actually post and get data from a server, which is the ESP32 as our current server for us currently. So the API that I'm actually currently using to communicate back and forth from the PC to the ESP32 is actually a REST API. So REST API is actually a text-based communication protocol, which is flexible and easier to actually debug compared to those binary-based communication protocol. This REST API is actually very flexible, as you can see the example on this screen, where I can only set this address as a mandatory input. As without the address, the microcontroller wouldn't know which LED set to actually go, as we have almost 32 sets of the LED afterward in the farm. So for others like name, LED state, red, green and blue is actually optional input, where I'm able to actually post it out. Without them, I'm still able to actually get a response from ESP32 without an error. So for this name, right, the name is actually used for the dashboard afterward, where we actually can show to the user that which ginger is which ginger. So instead of using the address name, we can use like ginger, the type of the ginger name like ginger ABC, different kind of ginger type. So the LED state we can set either the red, green and the blue. So the red we can set the power either on or off, intensity from 0 to 255, and then the cutoff temperature from 0 to 110. So red, green and blue. So this cutoff temperature, later I will discuss about it. So now let's start to set 3 LED together. Okay, now let's start to set 3 LED together. So for the left LED will be the green, middle will be the red, and the right one will be the blue, where we try to actually turn all on with the intensity of 20 on all 3 LEDs and cutoff temperature of 100. So let's see. So we change here on, and red, green and blue. So we actually try to change the intensity for blue to become 100, because we actually use a very small LED on the blue board, so that we change our high intensity so that we can see clearer. So this cutoff temperature is actually also used to set whether if the temperature is set higher than the cutoff temperature, so it will actually automatically turn off. So it is a sensor lah, but that one we will demo it later. So let's see. So we set. Okay, you can see the two LED actually light up. The middle one is the red one, and the left one will be the green, and then the right one will be the blue. So once it successfully sent out, actually it will return an OK message. So if the packet does not receive, it will return an address available. That one we will actually show it later. Okay, so let's see on the demo. Okay, so this one will be the green, this one will be the red, and then let's see the blue one. So because it's smaller, so we need to change it, to zoom it. You can see the blue is actually lighting up. It's a bit small. So we can actually change the blue back if we want to become a smaller intensity. So we change it to become 10, and then send. Okay, you can see the blue actually almost dim off, but you can see on the camera, if you use your eyeball to see, actually it's dimming, but it is because the camera issue. So we change back. Okay, so we return back here. Okay, so let's also try to actually turn off the red LED on the middle. So red actually turn off. Okay, send. So we actually can set the red become off, and then the intensity remain the same and the cutoff temperature. So as shown on the camera, we can see that the red actually turn off the middle one. So the left one is still the green, is still on, and the blue is still on, but it's a bit small. Okay. So, but as you can see on the red LED, you still see some small LED actually lighting up. It's because it is a hardware issue that I just mentioned just now, where the SMPS detects some of the voltage difference on the circuit, which is a circuit bug. We're going to fix it later. So we also actually can perform the individual tasks, like I just want to turn on my red power. I don't want to change my intensity and color temperature, so we can go to red body, and then we can change this one to become power, and then on. So we can send it out. Send. I can see the power is actually turned on back for the red. So this one is actually the benefit of customizing own rules using the REST API, where the user does not actually require to remember the previous value. Like I no need to remember what is my intensity or even my cutoff temperature, so that I just want to turn on my red LED. So I just give a command, give a JSON data with the power on, then it will be turned on. Okay, so third, I'm going to actually demo how the cutoff temperature works. So we're going to demo on the green box. So we set the cutoff body. So we go to green, red, and blue. So we actually can change the cutoff for my green. So I want to change to become 20. Okay. So it's so the cutoff temperature is actually, if it's higher than the current temperature, it will automatically turn off the LED. So let's try the green LED. So we turn on the power, and then we set the cutoff temperature to become 20. Okay, so we can see that the green LED actually dim it down. It's off now because actually the current temperature is higher than the cutoff temperature. So if you go to the get temperature, right, so we can actually get send. So we can get the value where the green is 35 degrees, but it's actually overheating. As you can see, because we set the cutoff temperature to become 20, so we can see that it will return a true overheating value. So if we try to revert back, so we go to a power, and then we turn on the green power, and then we change back the cutoff temperature to become 100. So we send. So we can see the green LED eventually turn it up back. Okay, still trying to retrieve the temperature of 3 LED. Okay, get temperature so that we can have the ESP32 local and get temperature address 1. So you can actually change to address 2. So this is actually an input parameter to indicate which address I want to get the temperature. So because we only have one set of LED, so that we only can get one set of data. So if I actually get the second address, so we return something like just now I mentioned, address unavailable. It's just like you disconnect the whole LED and then you cannot connect to the STM8 and the ESP32, from the ESP32 to STM32 and STM8. So you return back this address unavailable because you cannot get any data there. So we change back to 1. So we can see the temperature across red, green and blue RGB. So the red temperature now is like at 38 degrees, the green temperature is around 55 degrees, for the blue will be 25 degrees. So we try to get the voltage and current. Now we can see, so we try to send. Okay, so we can see the red current as 0.17, and green we don't see any current, but we will try to increase our intensity to see the current across it. So we go back to intensity, and then the green maybe we change to 50, and then the red also change to 50, but I need to turn on this one. On. Yes. Okay, so I send. So you can see the intensity become larger, and then we try to get the voltage again. I can see the current flowing through the red and the green, you see. And then the voltage is across is around 42 volt and 43 volt, which is normal. And then the blue one, because we actually does not have enough time to build the same circuit as the red and the green, so we actually use the 2 potentiometer. So you can see I try to adjust 2 potentiometer. Yeah. So we try to send again. Okay, you can see the blue value is actually different compared to just now. So now the current is like 2 ampere and then 40 volt, and the power is around 93. So lastly, okay, we also can actually set the time to enable it, so that when user want to get the electrical parameter like voltage, current and temperature, he will get the time. So now we're going to set the time now. The current time is around 3:41. So we set 3:41. Okay, we post to the set time. Okay, so we now are able to actually set the time. So you can see the JSON parser here on the console. Okay, and then we try to set the property. So we try to enable it enable it the tag with time. See, tag with time, and then we enable it. We set to true, and then we post to ESP32 again. Okay, so okay, and then we try to get the temperature now. The temperature. So we can see there is a clock there with the timer 3:42, and then we also try to get the voltage again, once again. Can see that the rate current is 0.27, and then voltage and power, and then lastly the clock will be shown on here. Compared to just now, before I start to set the time, you cannot see any clocks there, right? So after we enable it, you can actually see the clock. So this clock is actually used for like those dashboard or IoT system, right? When they actually request from the ESP32, which is a main LED controller, so they will see the time. So we can generate a signal graph or a chart through the time. So you can see how the current going up or going down, and then the voltage when users start to actually change the value, the intensity, or even the power. So afterward, after you enable this, then the clock will be attached on this get temperature and the get voltage and current, which is an electrical parameter lah. Okay. So that's all for my demos today. Thank you.